Okay, so we have one more gas law that you have to know how to use, and that is something called the ideal gas law. The ideal gas law was sort of a combination of some observations made by both Gay-Lussac and our old friend Avogadro. Okay, Gay-Lussac noticed that in the reaction between hydrogen gas and oxygen gas, which makes water, it always took 2 volumes of hydrogen and 1 volume of oxygen, and what we got was 2 volumes of water vapor. Okay, and then he started just messing with other gases, having gases react, and he noticed, this is what he noticed, that at constant temperature and pressure, volumes of gas reactants and products can always be expressed as small whole number ratios. Okay, so Gay-Lussac made that statement. Avogadro, and we talked about Avogadro's law before, he said that at the same temperature and pressure, equal volumes of gases contain equal numbers of molecules. And this just astounds me every time I hear it. It doesn't matter what gas we're dealing with. If we're dealing with a gas, 2 gases, and as long as they're at the same temperature and pressure, both of those gases will have the same number of molecules. And I think that's a God thing. I mean, it sure has helped us out in being able to figure out a lot of stuff. So anyway, Avogadro's law said that the volume of gases is equal to a constant multiplied by the number of moles of the gas. All right, and we've talked about this before, that the standard molar volume of a gas, it means what is the volume of 1 mole of gas at standard temperature and pressure. What's standard temperature and pressure again? Well, standard temperature is 0 degrees Celsius, standard pressure is 1 atmosphere, 760 millimeters of mercury. But that volume of 1 mole of gas, whichever gas we're talking about, is always 22.4 liters. If we have 22.4 liters of any single gas, we know that we have 1 mole of gas atoms or molecules. It's astounding to me. All right, so you have to know how to do these kind of problems. I want to erase it. It asks, what volume does 0.0685 moles of a gas occupy at standard temperature and pressure? Well, we know that 1 mole occupies this much, but we don't have 1 mole, we have this much, so we're going to do a little dimensional analysis. Start out with what we're given, 0.685, put down here 1 mole, 22.4 liters. What's the volume that 0.0685 moles of any gas occupies? Well, it's 1.5344 liters. So you should know how to do those kind of problems. You should know how to do these kind of problems. What quantity meaning moles, how many moles of gas is contained in 2.21 liters at STPs. It's just another little dimensional analysis problem. Start with what you're given, 2.21 liters. And it asks how many moles is that? Well, we know that we have 22, that 1 mole is 22.4 liters. So we're putting that on the bottom, marking it out. We get 0.1 moles. Okay. All right, and right here we just need to say the ideal gas law is that there is this mathematical relationship between the temperature, pressure, volume, and the number of moles of gas. And this is all because of Avogadro's law, that we can know how many liters, what volume does 1 mole of gas have. And it leads us to this relationship here. Here is the relationship. The pressure multiplied by the volume is equal to nRT. T being the temperature. N is the number of moles of the gas. R is the ideal gas law, or excuse me, the ideal gas constant. Okay? And here is that constant right there. All right, you should be able to use this equation. All right, and this is what relates the number of moles of the gas that we have to all that stuff we've been talking about. All right, so let's look at a problem here. What is the pressure exerted in atmospheres that is exerted by 0.5 moles of a sample of nitrogen gas in a 10-liter container at 298 degrees Kelvin? Oh, good, they gave us temperature in Kelvin this time. We don't have to do that calculation. Well, we start out with our We have moles of a gas, so we know we're dealing with the ideal gas law, so we know that this is the thing we're dealing with. It asks us, what is the pressure exerted? So we're solving for P here. So I've divided by V on both sides. Okay, so we get that the pressure is equal to N, which is again the number of moles, R, which is that constant, there up there at the top, T, which is the temperature, and divided by V, which is the volume. Okay, so N, well it tells us we have 0.5 moles, so that goes right in there. R is that thing. You will not have to know R. You will not have to memorize that number. I'll give you that number. Our temperature is 298 Kelvin. They give it to us in Kelvin, yay. And divided by our volume, 10 liters. So what we get is, that's going to give us a pressure of 123.9 atmospheres.